Welcome to Tech to Tech presented by KaiZen, where we will explore common cleaning questions and answers. Let's get started. I would like to introduce KaiZen's own Zach Papiez.
Good afternoon, William, and thank you to everyone for tuning into this presentation. This presentation is on utilizing tools that provide objective evidence to characterize a process and contrast different process conditions. This was accomplished in the context of a case study with one of our customers. Our company was approached by an aerospace and defense company to provide service testing for their process characterization, as well as a comparison of different process conditions. We were thankful to have the opportunity to assist them in this regard. The company was interested in comparing a variety of different testing conditions, including SMT paste selection, wasp condition, rework setup, wave soldering, and selective soldering. Conducting an array of testing, we were able to provide guidance on the process chosen and raise awareness on the potential cleanliness problems that can arise for a specified process. Our team was able to provide further valuable insights into the testing conditions and their impact on the process, and provide objective evidence to aid in their process understanding going forward. Characterizing and selecting a process can be challenging, especially when it comes to test selection and interpretation. There are many analytical and practical tests available that can provide either useless or difficult to implement data. It is important to ensure that the scope of the testing is sufficient to encompass the breadth of the test parameters. This includes having a large enough sample size to ensure that results are statistically significant. When it comes to test selection, it is important to choose tests that are relevant to the process being characterized also. This can include tests for cleanliness, reliability, and performance, among others. The interpretation of these tests can also be challenging, as there may be multiple ways to interpret the data. It is important to have a clear understanding of the goals of the testing and how the results will be used to ensure that the correct conclusions are drawn. Elaborating on this further, you must match the test to the problem. In order to do this, it is helpful to ask yourself a few questions. Firstly, you should ask yourself, what am I testing for? Focusing on this will help you identify the most appropriate test for your needs. Once you have identified the tests, it is also important to ask whether the tests will detect problems in your process. This can include issues related to cleanliness and reliability. By selecting the right test and ensuring that it is capable of detecting problems in your process, you can ensure that you are able to make informed decisions about how to optimize your process going forward. When selecting the test, it is also important to ensure the scope of the tests is large enough to catch as many failures as possible. This includes covering all the conditions for your process and ensuring that each condition is covered sufficiently. By doing so, you can ensure that you are able to identify any potential issues with your process and take corrective action as needed. Knowing how to interpret the data is also important. This can include having a known fail condition and can be used to validate the results of your testing. By having a clear understanding of what constitutes a failure, you can ensure that you are able to make informed decisions about how to optimize this process. It is also important to consider the limitations of your testing and how they may impact the results. By taking these factors into account, you can ensure that you're able to make the most of your testing and achieve the best possible outcomes. As mentioned previously, the process that was examined includes wave, selective, and rework procedures. Objective evidence is required to provide insight into these conditions. Basic examples of selective solder and rework are also shown on this slide. Sometimes the rework process is as basic as re-hand soldering at the end of a PCB process. There are a wide variety of process changes that can be derived from this. An array of surface insulation resistance testing with supplemental IC testing was chosen to add insight into these processes. 4 sets of data was gathered each for every condition. IC was specifically chosen for the test vehicles labeled MAG 11 through 14, given the known dangers for rework without washing. SIR was opted for every test condition to fully characterize and contrast the wide range of test conditions and their electrochemical profile. The test vehicle chosen can be seen here. It is a Magnalytics test coupon with dummy components used to represent the components with the most challenging reliability profiles. This particular board comes with a variety of components with SIR cone patterns. We find that the QFN and BGA with the center lug are typically the most difficult parts to reflow and clean. The board is also double-sided to better represent an actual production board that one might run through an inline cleaner. Also pictured is a typical example of an auto-sampling ion chromatographer. It is able to precisely characterize the ionic contaminants on a test vehicle as well as generate its own standards to increase accuracy. One of the most striking findings in our data analysis emerged when we explored the combined effects of rework condition without washing after the fact. This condition produced highly noteworthy results within the context of our study. The data from this SIR measurements provided compelling evidence of the presence of leak currents. These leak currents were manifested as distinct downward spikes in the reported data, a phenomenon that strongly suggests the occurrence of dendrite formation within the components under investigation. Dendrite formation is a critical concern as it can lead to electrical short circuits and compromise performance in various electrochemical systems. Therefore, the clear identification of these downward spikes underscores the importance of addressing and mitigating the risks associated. In addition to the concerning SIR data findings, this particular board is also presenting compelling visual evidence of active residue. It's worth noting that the component under scrutiny in this case was the BGA 244 with the center lug. The simultaneous presence of both visual residue and poor SIR data strongly suggests a connection between the two. It is highly likely that the decision not to perform a thorough washing process after initiating the rework procedure had an adverse impact on the overall quality and performance of the board. This observation underscores the importance of meticulous cleaning processes and careful consideration of rework methods to ensure the reliability and functionality of the electronic components and boards. Furthermore, the application of ion chromatography provided additional information on the existence of active flux ions within the board. This analytical technique allowed us to detect and quantify these flux ions, adding depth to our understanding of the board's condition. Particularly noteworthy were the acetate levels detected during the ion chromatography testing, which fell within a borderline range. This finding raises further concerns about the board's overall performance and suggests that the presence of these ions may be affecting its functionality. The evidence of acetate in the measurements underscores the importance of monitoring and addressing flux-related issues to ensure optimal operation and longevity of electrical components and boards. The next slide shows the SIR data from a board with the same process conditions with the addition of a cleaning step. All values gathered were above the 9 log ohm range in what we call the desired performance zone. This board is void of any of the jagged and erratic lines shown in the previous slide. It no longer shows any evidence for leak currents or any electrochemical changes on the board over time. This is an ideal SIR spectra. The image under the component for this board similarly showed much reduced flux residue and no trace of the white residue pictured on the previous board. The cleaning step clearly was able to make a difference and remove much of the visible active residues. The combination of surface installation resistance testing and ion chromatography emerged as invaluable tools for evaluating the potential risks associated with various process conditions. In particular, the processes that involved the rework procedures were found to be in need of an additional crucial step, namely a thorough washing process. These analyses revealed that active residues, notably those derived from weak organic acids like acetate, could persist on the board, or the oxygen barrier from these no-clean pastes could be damaged when rework was undertaken. The objective data obtained through SIR and IC played a pivotal role in substantiating the necessity of including a cleaning step within these processes. This underscores the importance of relying on empirical evidence to inform best practices, ensuring the integrity and reliability of electronic components and boards in complex manufacturing and rework scenarios. Next, let's look at a few commonly asked questions on the topic. Firstly, how does rework introduce more potential failures into a process? Because of the variable nature of how rework might be accomplished by an operator, it leaves a lot of room for human error or inconsistency. There will be much less transparency into the exact method used. The operator might inadvertently damage the protective oxygen barrier formed on the no-clean SMT paste also. Secondly, what are acceptable limits for IC? The exact acceptable limits for assemblies is not set by the IPC or other similar organization, but generally accepted limits for particular solder types, in this case no-clean, are used for most labs. Thirdly, how does SIR provide objective evidence? For one thing, SIR is able to quantify the resistance on a board. This is of greatest value when a dramatic and quick change in the resistance is observed over time, which should be a strong indication that something went wrong with your process. Thank you. That concludes my presentation, and I'll hand it back off to William.
Thank you, Zach. Thank you guys for watching this Tech to Tech session. If you would like to discuss this topic further or have any questions that were not answered during this session, please contact your local KaiZen regional manager or send an email to tech2 tech@kaizen.com, and we will have someone follow up with you as soon as possible. To download the case study this session was based on, click the link in the description below. Do you want to have exclusive access to future content sent directly to your inbox, or do you know someone who'd benefit from these sessions? If the answer is yes, just go to tech2tech by Kaizen.com, fill out the subscription form. And if you like this video, be sure to follow us on our social media platforms for more expert cleaning content.